or finitely.
Thank you very much for introduction. So today, so Zoom participants, can you hear? I don't know. 望月さん、辻村さん、聞こえてます？
聞こえてます。聞こ
えてます。はい。
ありがとうございます。
はい。
So today I'd like to give a talk on M-step solvable anabelian geometry of finitely generated fields, where in usual anabelian geometry we have the group profinite group in question, fundamental group, so absolute group, Galois groups. But the M-step solvable version is this group in question is replaced by the maximal M-step solvable quotient. Yes. But now here we have so together with Mohamed, I established the result for the arbitrary finitely generated fields. But there are two parts, and the global fields case, namely number fields and the global function fields, and the higher transcendence degree case. And so that today I would like to rather concentrate on the latter part, and I will give a quick survey on the first part. This is because I gave a talk on the first part in overall half a year ago, but now I realize that the only participant there is Hoshi, and so that I could repeat the same talk, but anyway, so today I would like to stress on the transcendent higher transcendence degree case. And also, as the first speaker, I would like to give a I have to start slowly, and I would like to give some necessary things for anabelian geometry, and I would like to especially relate some parts of my talk with other parties, other talks. Yes. Okay, so let's go. Okay, so this is the contents, and this is the section 0 and section 1. As a review, and the review of notions and policy philosophies and main results so far. And then the section 2 is our main result, and section 3 and section 4 are outline of proof. And now as I mentioned, the section 3 is very short, and I would like to stress on the section 4, namely the higher dimensional case. Okay. So first, I would like to start with anabelian geometry. Of course, this workshop is concerning the recent advances in anabelian geometry, and so it is not very good to start with what is anabelian geometry, possibly. But anyway, so just quick. In the early 80s, Grothendieck proposed anabelian geometry, and his original motivation of anabelian geometry is the second one, anabelian geometry in the wider sense, and namely he constructed in scheme theory in EGA or SGA, but of course by the very definition, the definition of schemes is based on commutative links, unitary commutative links, with two operations, plus and multiplication, addition and multiplication. But he considers that considering the fundamental group, profinite étale fundamental groups, he pointed out the possibility of reconstructing the category of schemes purely based on the profinite groups. Well, this big scheme is what Grothendieck considered originally, but as a piece of this anabelian geometry in the wider sense, the first question is posed by also Grothendieck, namely anabelian geometry in the narrow sense ask ask us to reconstruct the anabelian schemes purely group theoretically from their profinite pi1. Profinite pi1 is et al. Pi1, and there is no definition of anabelian schemes, but so the anabelian the role expected role played by anabelian schemes is affine schemes in usual scheme theory. Namely, there is the fundamental piece of schemes, and then the general schemes should be obtained by patching together anabelian schemes, and so this is a local thing, and he did not give, and in fact we did not get yet the exact definition of anabelian schemes, but there are several varieties or schemes which are considered to be anabelian, or which are proved to be anabelian. Yes. Okay. So and here in this talk, I would like to mean anabelian geometry in the narrow sense, in the first sense, but just by saying anabelian geometry or even AG. Also, I would like to mention the complement of the second wider anabelian geometry minus the first narrower anabelian geometry, namely in order to reconstruct the category of all schemes purely group theoretically based on profinite groups, an important problem is to reconstruct the absolute Galois group of the rational number field Q. And this is related to the combinatorial group GT and the related theory, and which is, for example, given in the talks by Roshak, Minamide, Tsujimura, and also related to other participants' talk. Yes, but here this is rather the wider sense, and then and also in the case when the scheme in question is a spectrum of a field, then in this case sometimes it is called a bilateral anabelian geometry, and then the pi1 of the spectrum of a field is an absolute Galois group, and here this theory has been investigated at least say 20 or 15 or 20 years before Grothendieck proposed anabelian geometry. And in this talk, I would like to only consider anabelian geometry of fields, even of finitely generated fields. Yes. Okay, and let me mention. In fact, in my talk, I wouldn't like to go thoroughly into this distinction, but to specify the standpoint of the talks in this workshop by other speakers, I would like to mention the following. First, the anabelian geometry in the narrow sense is reconstruct anabelian schemes. What is reconstruction group theoretic reconstruction? That is there is a room for interpretation of this reconstruction, group theoretic reconstruction, purely group theoretic reconstruction, and yes, and so the first first notion is mono-anabelian geometry. Mono-anabelian geometry. This is rather naive, and it requires many tasks to formulate rigorously, but still it is very important and close to our our feeling is mono-anabelian geometry, and here is so possibly did here I omit I erased incorrectly some phrases because lowercase letter starts with, but anyway, so here the main point of mono-anabelian geometry is to find purely group theory algorithm. Starting the input is a ether fundamental group of scheme, anabelian scheme, and the output is a scheme X itself, or a scheme more precisely a scheme isomorphic to X. And then the point is we find out the purely group theoretic algorithm for reconstructing X starting from the pi 1 of X. This is the idea of monoanabelian geometry, and this is very important and related to other guys. And the next one is bi-anabelian geometry. This is rather easily formulated. But it is known that it does not grasp the whole monoanabelian geometry. But let me start. So the bi-anabelian geometry is here we consider the two schemes x1 and x2, and then the say isomorphism between pi 1 of x1 to pi 1 of x2 is in one-to-one correspondence. In fact, up to conjugacy by due to the ambiguity coming from base points, but isomorphism pi 1 of pi 1 is in one-to-one correspondence with the isomorphism between scheme or the original schemes. This is a bi-anabelian geometry, and so that we can formulate this as by setting some suitable categories and some functors, and then this functor is categorical. It gives free faithful or something like that. Okay, so this is a bi-anabelian geometry, and so it is. Of course, it depends on the category of some category of schemes, and also the we sometimes we may have to consider some variants, but this is basically it is standard and straightforward to formulate this bi-anabelian geometry. Yes. And also the variant is home version. Home version is here I only consider the isomorphisms, but we can also consider the homomorphisms of schemes. Yeah. Okay. And so the isom version, but isom version of bi-anabelian geometry, it can be viewed as a special case of home version of anabelian geometry. Home version of bi-anabelian geometry. Of course, home version is usually bi-anabelian. Okay, and finally, the weakest version is weak bi-anabelian geometry. This is again given two schemes. So the weak bi-anabelian geometry hopes that if the two schemes, if the pi 1 is isomorphic to each other, this is not S1, but this is x1 and x2, and the original schemes are isomorphic. Yeah, this is a weak bi-anabelian geometry. And so bi-anabelian geometry, of course, implies weak bi-anabelian geometry, and also monoanabelian geometry is so the groups, of course, we have to specify what is the meaning of group theoreticity. But if we start with so we have some group theoretic algorithm to reconstruct this, and then some steps, and then 望月さんと辻村さん見えないと思いますけど、すみません。And then here is the same algorithm. But group theoretic means that if this is isomorphic, then everything is just done by only by using the group operation, so that this is isomorphic and this is isomorphic and this is isomorphic. So both monoanabelian geometry and the bi-anabelian geometry basically implies this weak version. Yes. But in this talk, I don't care about the difference, subtle difference among these three or four notions, and anyway, so so that I would like to use reconstruction or recovery in the very naive sense, and so reconstruct anabelian schemes. What is the exact meaning of reconstruction is not specified in my talk, and I just write pi 1 x reconstructs x, so like this by squiggle pi 1 x square. Sometimes this means monoanabelian or bianabelian or even weak bianabelian, but basically our result is bianabelian result. Okay. And then another distinction classification is absolute version and relative version. And the absolute anabelian geometry is just as I explained, and consider schemes and the étale fundamental groups, namely which are profiling groups. So that we consider the some category of schemes and some category of profiling groups. On the other hand, relative anabelian geometry is first fix a base scheme S, then consider the schemes over S and the profinite groups over pi on S. Profinite groups over pi on S is a profinite group which is equipped with the homomorphism, continuous homomorphism to pi 1 of S. Then we consider that these two categories. This is relative. So, for example, when we consider the category of varieties, then it is in some sense natural to consider relative version. Okay, so why I would like wanted to mention these classification is I would like to summarize the three talks in anabelian geometry, pure anabelian geometry in this workshop. So my talk is M-step solvable version. So I mentioned the M-step version of absolute and bi-anabelian geometry fashion of finitely generated fields. So the scheme is finitely spectra of finitely generated fields, and the bi-anabelian version and the absolute version. There is no base scheme. Okay. And Hoshi's first talk after my talk is a relative version, namely he is considers a variety over some field, and then he considers section conjecture. Section conjecture is a home version from a point to some variety, and relative version. And so and he especially considers the variety to take hyperbolic polycarbs. This is higher dimensional varieties and expected to be anabelian and even by biocrotantic. And the Mao's talk on the last day, on Friday, is again M-step solver version of absolute anabelian geometry of number fields, but the typical feature in Mao's talk is he treats mono-anabelian geometry. So that this is my talk and Mao's talk are related, but I'm only considering bi-anabelian geometry, while Mao's talk is concerning mono-anabelian geometry. Okay. And finally, in the introduction, I would like to tell a rough pattern, the pattern of proof in anabelian geometry, typically which can be seen typically. And this is distinguished with local theory and global theory I named, but both naming are not so good. And but for simplicity, I would like to refer to these two theories as local theory and global theory. And the first local theory is what? So we consider the schemes. Scheme is the spaces, and spaces consist of points or the other small pieces of spaces, and then by the usual procedure in Galois theory, each such substructure points or the points determines a subgroup of the pi 1, which is called the decomposition group. This is standard in Galois theory. And so we have the natural map from the set of points in some sense to the set of subgroup, closed subgroups. And the separatedness it means that this map is injective. So first step is sometimes to show the injectivity of this map, sending each point to the decomposition group. And then why this is important is because the set of points are just geometric, and so here I mentioned that in the mono-anabelian reconstruction, X is not may not be the original X, but the scheme which is isomorphic to X. So we have to reconstruct by using the pieces or ingredients coming from this group, and in order to get the set of points, then we have to send the set of points in faithfully in some sets coming from the pi one, and so this injectivity shows that the set of points are faithfully represented as a set of set of subgroups of the fundamental groups. Yes, and then the second step is reconstruction of decomposition groups. This is to group theoretically detect what this subset of group, a set of subgroups of pi one. So namely, which group is decomposition group. So to detect which subgroup is decomposition group. This is the important step. And then if we got these two steps, then we got the reincarnation of the set of points inside pi one, and then some other various local invariants and so on. And here the global theory. This is not global theory, but the global theory is basically by using this local theory, we reconstruct the fields or schemes itself. So this is, but this depends on the situation. This local theory sometimes has some similarity in various settings, but the global theory usually depends on the situation, and so that okay. And then let's start. And the notation is like this: P is a set of prime numbers, and sub gamma or profile group. Sub gamma is a set of closed subgroup, and the set of open subgroup, and the maximal pro L quotient, maximal pro prime to L quotient, abelianization, and the maximal pro solvable quotient, and here the maximal m step solvable quotient of gamma. So the quotient of gamma, whose the maximal quotient of gamma, whose m's derived series is trivial. Yes. Okay. And then first before explaining the m-step solvable Anabelian geometry of fields, I would like to review the Anabelian geometry of fields, finitely generated fields, very quickly. Okay. And the global fields case is the famous theorem of Noikiri-Uchida for number fields and then Uchida for function fields case. Namely, starting they succeeded in reconstructing the number fields or global function field starting from the absolute Galois group. Okay. And here the local theory separatedness comes from the approximation theory or the and especially the Grunwald-Wang theorem. Classical Grunwald-Wang theorem gives a separateness. And also the group theoretic reconstruction of the decomposition group comes from local global principle for H2. This method is introduced by Neukirch. And this local global principle for H2 is local global principle for Brouwer groups, which have an important role in class field theory. And then the global theory is quite different in these two cases. And function field case is by class field theory, and which has demand. This is quite simple, and this gives rise to even the mono-anabelian reconstruction algorithm. But in the number field case, it is rather complicated in some sense, and the mono-anabelian reconstruction algorithm was first given by Hoshi, and this part is related closely with Mao's talk, I think, and so the please expect the last day talk. Okay. Then this is a case of global fields. And then the arbitrary finitely generated field case. And then here the K is a finitely generated field over the prime field F. F is Fp or Q. And but the TDK means the transcendence degree over the prime field, and the Kronecker dimension is defined by this formula. Namely, the Q. The point is Q. The number field has dimension 1, and the finite field has dimension 0, and almost transcendent degree. And then the Florian Popp proves the following. Starting from the absolute Galois group of finitely generated fields, he succeeded reconstructing the field itself in characteristic 0 and its perfection in positive characteristic. In fact, it is well known that even if two fields are not isomorphic, if the perfections of these two fields are isomorphic, then the absolute Galois groups are isomorphic. So this is best expected, and so in higher dimensional case, we cannot expect that we could reconstruct K itself. Okay. Okay, so this is a big theorem, and now the very rough outline of proof of Popp's theorem is as follows. And so here we resort to the heavily the theory of valuations, and so the terminology on valuations I would like to postpone till section 4. So that if you don't know the valuation theory, then the please expect till section 4. Yes. And first is this is very rough steps, but first step is he reconstructed the set of defectless valuation of rational rank I. So this is quite difficult notion in valuation theory, and its set of decomposition groups for each I. And then the proof of this reconstruction is some sort of reminiscence of no-given method, and he proved and resorted to the certain type of local global principle for H2. But this H2 local H2 Hasse principle is quite new in the higher dimensional, higher transcendental degree finitely generated field, and so and he in the proof of this local global principle, Popp resorted to model theory and theorem elementary equivalence and ultra products. And then he characterized so-called geometric divisory valuations inside the defector variations of rational rank 1. And then also he detected the which subset of divisory variations is geometric. Geometric means that basically comes from some model of fields. Yes. And then the global theory is he interpolate local data by using induction. So in the one-dimensional case, it is Noiki-Uchida or Uchida theorem is available, and so by using induction, the result we can assume the result in lower dimensional case, and then he patch the additive structure or the field structure from the divisor to the field in question of dimension D. But here he also used the model theory. Yes. And then now the why variation theory. In fact, in the case of anabelian geometry of curves or one-dimensional fields, we can only consider the set of points in some schemes. But here, in the higher dimensional function field, the model is not unique, and so if model is changed, then the set of points or set of divisors are changed. And so the points or divisors are not very standard notions for the absolute Gala groups, and more intrinsic structure is variation theory and decomposition groups of variation theory. So that it is variation theory is not very much like arithmetic geometry, but here the considering the variation theory is a very natural way of considering the birational anabelian geometry of higher dimensional fields. And also the alternative proof in the special case is given by Spieß. So I made a mistake, and Spieß. And character 0 and Kronecker dimension 2 case. Here's a non-standard proof of Pop's theorem. And here's he resorted to the local, in his local theory, he resorted to the certain local global principle H3, and which is due to Kazuya Kato. And then the global theory, he didn't use the patching by using model theory or ultra product theory, but he just used usual algebras or the scheme theories. Yeah. And basically, our proof of the main result is more, in some sense, a hybrid of Florian's Pop's result proof and Spieß results. Yes. Okay. Now the main result. Here's the notation for m-step solvable quotient. Gamma bracket m is a m-derived subgroup, and gamma upper m is the maximal m-step solvable quotient. And then the gamma mn is this intermediate quotient. And then this is slightly complicated, but if we are given a subgroup of gamma m-step solvable quotient, then we denote by f tilde or f tilde I for the inverse image of f in original gamma or gamma m plus I. So this plays a very important role in our theory. Okay, the main theorem is as follows, and so K is a finite general field over the prime field. Then there exists some positive integers depending only on the Kronecker dimension, such that if m is sufficiently large, m is larger than or equal to m naught, then the K can be reconstructed purely group theoretically from GK to M, the maximal m-step solvable quotient. And oh, what is this? This is just mistypeset. And for the present, in the global field case, global field case, we can take M node is 2. Namely, for example, the metabelian maximal metabelian quotient of absolute Galois group of number fields or global function fields have the information on the field itself. Okay. And in the higher case, we have to take 9 or 8 or 9. This is somewhat big, but a few years ago, our result was here the M node D depends heavily on D, so that D square plus something, and so that now that this is constant and we are somewhat happy, right? Okay, and just a notation, but Km is the corresponding Galois extension of K corresponding to GKM. Yes. Okay, so the maximal M step solvable extension of K. Okay.
Oh, sorry.
Yes, please.
So your remark is saying that in fact it doesn't depend on D, it's just 9 equal to 9. Is that what you're saying?
Nine, it does not depend on D.
Right.
Yeah. So that this is an improvement for some years ago. This value M not D heavily depended on D, but we improved the result, and now it does not depend on D.
So in the main theorem, it actually doesn't.
Sure. Yes, thank you. Yes.
The 9 is valid for all t bigger than 1.
Yeah. See, of course, the two can be replaced by 9 if you like, but so then the 9 is constant, but the yeah. So I stated as such, yes. So there is an absolute constant, namely 9, such that if M is at least 9, then the GKM reconciles. Okay. But for the global field case, M not equal 2 is enough. Yes. Okay. And the global field case, the new point. So this is very quick, and the new point is in two directions. And the first point is the modified so script modified cohomology, and namely the so this is a we start with a closed subgroup of GM. So GK, say this is GKM. Then we have to detect whether or not this is decomposition group. But we cannot resort to the full H2, full Bra group corresponding to the field, because we can only use the M-step solvable quotient. And so instead we introduce the one step higher. So this is H is a M step the subgroup of GM. Then the H1 is the impulse image in GM plus 1. Yes, and then take the inflation image. But then this is enough, and so this lemma shows that the one step, if it is killed, the kernel to this is H tilde is in G, the full G, but if some element of H2 is killed in the inverse image in G, then in fact it is killed in G M plus 1, so one step higher. So here we can limit, restrict the usage inside the finite step. So one step is lost, but still the finite step. And then the next definition is the crucial thing, and so star L1 condition, and this is the extension subgroup of F in GKM, which is a semi-direct extension of ZL by ZL, ZL by ZL, and such that this script cohomology is non-trivial. Then this is local global by using the local global principle of usual H2 plus this lemma, we can establish that if it satisfies these conditions, if and only if F is an open subgroup of an L0 subgroup of a decomposition group of GK. So that we need some more work to reconstruct the full decomposition group, but this is the very important first step. So these two script cohomology and by using the local global the characterization of the at least L0 groups of decomposition group by using this script cohomology. These two are the main new inputs. But here, I think that these techniques may be revisited in Mao's talk, and so let's see. Yes. Okay, so this is a global case, and finally, I would like to explain the case of finite degenerate fields. But here, it is complicated in valuation theory, and okay. And then the SPBK is a set of valuations of K. So that it contains a trivial valuation. And then it is equipped with a natural topology. And then it is known that this is quasi-compact T-naught space. And also the absolute value means a set of closure points. But this is known to be a quasi-compact T1 space. Okay. And in fact, the set of closed point coincides with a set of valuations whose residue field is algebraic over finite field. Okay, and for each valuation, gamma b denotes the value group, and OB is a valuation ring, MB is a maximal ideal, kappa b is a residue field, PV is a characteristic of kappa V, and here the rank. Rank is the rank of the ordered abelian group gamma B, and which is equal to the cardinality of spectrum OB minus 1. So that in the DBR, in the case of this minus 1 is no, sorry. I made a mistake. So that this is, sorry, not the minus 1. This is itself. I'm sorry. So in the DBR case, no, the 2 minus 1. Okay, I'm confused. Sorry. This is correct. And so the rank is there's a notion of rank of ordered abelian group, and which is equal to the cardinality of spectrum minus 1. Okay, and the rational rank is the value group, the rank of value group tensor Q. Okay, and Henselization. Here's a Henselization. And then it is known that the rank does not exceed rational rank, and the sum of rational rank and the Kronecker dimension of the residue field does not exceed the Kronecker dimension of the original field. And the defectless, B is defectless if is said to be defectless if bracket 2 holds, and B is rank defectless if both 1 and 2 holds. So this is it is difficult to grasp what happens, but there's please consider that these rank defectless valuation is a good valuation. Yes. And D is defectless, RD is rank defectless, and the upper I is rational rank, and rank equal I means, yeah. So only I means refers to rational rank. And L prime means the residue characteristic is not L, and div, the set of geometric divisorial variations. Divisorial means the rank 1, and the PB equal P. This means that residue field is the residue characteristic is the same as the characteristic of the base field. So this means geometric in some sense. And the set of space of valuations admits the ordering, namely, so given two valuations, B is less than or equal to W if the various calculation W is contained in the closure of B in the topology of SPB, or this containment of variation ring, or the opposite containment of the maximal ideal, and so on. And also we have the composite of valuations or quotient of valuations, and so there are several steps of, but in the case of higher rank valuation, we have the various operations, yeah, and so this so dimension one case only the trivial variation and rank one variation only exists, and so that this ordering is very simple. But in the higher dimensional field case, the ordering is very complicated. Yes. And also that there is a Galois theory, and so that I would like to be quick. And so that for each valuation and the extension in the Galois extension, we have the notion of decomposition group or inertia group, or the wild inertia group or tame inertia group, and as in the case of the usual scheme theory or the field theory. Yes. And then the tame inertia group is isomorphic to the product of the ZL1, the Tate twist, and but here the rank of ZL depends on L, may depend on L, and this is a dimension of gamma B modulo L, and which is by definition it is does not exceed rational rank. But in the good case, namely K is finitely generated, B is defectless, and then it is known that gamma B is finitely generated free abelian group, and RBL coincides with rational rank, and kappa B is finitely generated field. So that this is good case, yes. Okay. And what we resort to or exploit this is a local global principle we exploited, and the Grunwald-Wang type theorem due by Lorentz Rocket. Here except for the classical Wang condition holds. Yes, assume the one condition holds. Then the basically the local Galois extensions, local abelian extensions can be approximated by the global Galois extension if we are given a finite subset of rank one valuations. Here the rank one is very important, and if we have a higher rank, then the and if two valuations are given and the two valuations are different, but these two valuations have the non-trivial common coarsening, then this sort of result is not available. So that we can, this sort of approximation of theorem is only available in the rank one variation case. Okay. And also we need the input from Galois cohomology. And here the first this is the reminiscence of script cohomology, and what happens? H1 this is script cohomology coincides with the ultimate cohomology, true cohomology. So this is a inverse image in the original G, and this is EG. And then I would like to review quickly the block-Kato isomorphism. namely F is an arbitrary field, and then we can consider the Milnor K group for each non-negative integer n, and which is represented by this sort of symbol, and the sum of this sort of symbol. And then this cohomology Hn of Gf Galois cohomology is isomorphic to the nth Milnor K group modulo n. So this is a very by the explicit application mapping like this. And so this is a very deep and important result in Galois cohomology theory, and which is available for arbitrary fields. So this is a very strong result. And then by using these two methods, oh no, yes. And here's a in fact, the usual definition of script cohomology is not so good in the higher dimensional case. And here, instead, we consider only the cohomology class comes from the cup products of H1. Yes. And then consider, and here we need extra not one step but two step, but then we consider this special type of cohomology class, and then I consider the image in the two step further, two step after two step. Then here the similar result is available, and then this script cohomology is injected mapped into the ultimate cohomology. H tilde is the inside the full Galois group. So that we can in the local global principle, we can resort to the disk cohomology. We can use this cohomology, which is computed within the finite step of solvable m-step solvable quotient, and instead of this true cohomology by using the subgroup of the full absolute Galois group. Okay, and here basically it is due to the H1 and H2 we already mentioned, but here by the very definition of Milnor K group, Hn can the class coming from H1 is the relation is described by using H2 relation. So basically H1 and H2 are enough to compute Hn. So this is under H1 and H2 the script cohomology works well, and so by combination this injectivity is available. So this is a basic idea. Okay, so then we would like to use this script cohomology, and we would like to resort to the local global principle in the higher degree cohomology. And here it is. This is a higher dimension cohomology, and so that D is a Kronecker dimension. Then we have this injectivity, and so D plus 1's cohomology and Galois cohomology, and then this is here L, but this is a periodic part and somewhat difficult. But the other part is not the prime to L part, and so this is the usual local cohomology, and then this is injective. And yes, this is basically based on Kelt's Saito, but they only use they only proved this result in the regular case, but then the alteration, the subtle variant of alteration gives this statement. Anyway, so the HD plus 1, the local global principle for HD plus 1, this is what we are using. And also here, this is still at the level of finitely generated field, but we need to apply this sort of result for the arbitrary closed subgroup of GKM. Then the corresponding field is not finitely generated, but only transcendence degree finite. But then basically it is treated by using the limit argument. But in order to make the limit argument work, we need some quasi-compactness, and here this is a quasi-compactness lemma. Okay, and then for arbitrary transcendence degree finite field, we have this sort of local global principle. Okay. Now our local theory is by using this, and the script cohomology is available, and this local global principle for the HD plus 1 is available. Then as in the global field case, we can reconstruct the decomposition group. And this is the last slide. And then the first, the defectless rank D evaluations, a set of defectless rank D evaluations reconstructed by using the group, the pro-L subgroup of type star L. Sorry, I'm sorry, star LD. So the semi-direct extension of ZL by ZLP. And this is a L part of term inertia group of rank D defectless valuation. And then the script cohomology is 0. Then by using this, this is related to the rank D defectless valuations, and so that we can reconstruct the rank D defectless variation by losing a few steps. But then we can reconstruct rational rank D, but the rank 1 valuations. Here, I'm sorry, this is, so that this is not M plus 4, sorry, M plus 4. This is an old version, the M plus 4. Here is M plus 4, yes. M plus 4, and this is a M, I'm so sorry. And then the rank 1 variation, and this is we need some complicated arguments, but by using rank D defectors, we can rational rank D defector variation, we can reconstruct rank 1 variation. Then finally, we can reconstruct rank defectless variation of rank I by losing 5 steps. And now by using these results, we can basically by the method of Spitz, we can reconstruct the field structure of the original field K. But here, by avoiding the too many losses of steps, we excluded the induction arguments, and instead, for valuations, we use rank defectless rank 1 valuation. 0 means that the residue characteristic 0. But we also consider evaluations or reductions for the rank D minus valuations. So these are split. And in the Spitz case, these are same. But by using this, we can avoid any induction step, and basically the M plus 5 or M plus 6 is enough, or something like that. And here the 3 steps are more 3 step or 4 step is necessary, and in conclusion, 4 plus 5 or 3 plus 5 is necessary to reconstruct K. Yes. Okay, and the last 3 pages are just references. Thank you very much.
It seems to me that your proof it seems to me that the proof of the finite generated field case is automatically more than Is that correct?
in fact, there are several parts, which was not made mono-anabelian, but still bi-anabelian.